And then today we are on functional programming. So basically, so far we have been working on different programming paradigm. Okay, you try to learn programming language, right? And very important is that you try to learn the paradigm. And what is paradigm? This one actually, I'm not sure what is your first name? What's that? Haiti or what? Can you answer me? What is paradigm in terms of programming language? When we talk about programming paradigm, what is paradigm? We do have event-driven programming. We do have structured programming. We do have object-oriented programming. We do have today functional programming. We do have logic programming, right? These are different paradigms. And what really is a paradigm? Do you have idea? No? How about Matthew? Do you have idea? We are discussing, okay? So
And
don't feel bad. Yeah.
is it just the method of how you program?
Yes, it's the way you do programming, the way you think.
No.
Okay. Okay. So in a way, neural network is also a paradigm. We do computing by mimicking the natural neural network, right? And we set up artificial neural network to mimic it. So basically, paradigm is the way you do computing. By what? By the way you think, right? You believe that if our neuron that we build by software or hardware can mimic the function of the natural neuron, then we can do as complicated things as the natural neuron, right? That's the fundamental belief. So this is a paradigm. When you set up the neural network, you are thinking about this, right? So then we do have imperative programming, and imperative programming including the so-called structural programming. So in the old days, 1960, we had the structural programming. It talked about if then else, and then while loop, and then for loop, and then repeat until, those kind of loop and functional code. Okay, that's been good for quite a while. C language is dominating that. Okay, that's good. Then C++ and Java come out with the idea of object-oriented programming. So we actually hiding the data into a module, and then we can use the object-oriented programming idea to build up larger library for graphic user interface. So good. Okay, now in the 1985, we start to have the Windows 1, Windows 2, 3, 4, 5. We start to have the internet computing. So we do have object-oriented programming. That's fine, good. That's actually have been good all time until 2015. Then until 2000, maybe 7. Okay, before that, that's actually pure internet area. And then after that, we start to have cell phone. 2003, we have iPad, and then iPad and whatever coming out, and then we do mobile computing. So this kind of the object-oriented programming for Windows is no longer enough. So we start to have event-driven programming. We start to have the gesture calculation. We start to have the drag and drop and those kind of things. And then it's a event-driven programming. And then we start to see the language of Swift or some other toolkits, right? X2 or whatever. And then 2015, we start to look at AI. So AI language, this event-driven programming is no longer powerful enough. So now comes the functional programming. But functional programming is not imperative programming. It is declarative programming. Okay, it is different. It's not line by line. It's not step 1, step 2, step 3 type of programming. It's function calling function type of programming. So today we are going to look at the concept of functional programming, pure function, recursion, referential transparency function, first class function, higher order function, and immutable variables. Okay. So first one, programming has imperative programming and declarative programming. Functional programming is belonging to declarative. So function calling function, okay, it's not line 1, you do this, line 2, you do this, line 3, you do this. If line 1, line 2, line 3, you do something like a recipe, like a menu, that's called imperative programming. So imperative programming basically is procedural, like C language, object-oriented, like Java. Okay, those are imperative programming. Python can be considered as imperative programming, okay? But now we are looking at the other aspect of the Python that actually is functional programming. So functional programming typically is Lisp, Sketch, Haskell language, Erlang, okay, this kind of language. And then one of the homework, we do need to work on the scheme language, okay? We do need to work on the scheme language. So declarative language means that you don't rely on the line 1, line 2, line 3, line 4, step 1, step 2, step 3, step 4. Step 4. Instead, you rely on the calling sequence. Function, calling function, calling function, okay? So in terms of the 4 major programming paradigm, imperative, you have C, C++, Java, Python, Arduino, okay, whatever, PHP. Object-oriented programming, you have C++, C#, Java, Python, whatever, Ruby, Scala. Declarative, you have SQL database type, okay, or you have functional, you have scheme, Haskell, or Camel, Python, okay? So these are different languages. Functional programming language, let's look at this, okay? So basically you have imperative programming, you add the abstraction and then you become software IC, okay? It's become software IC, it becomes library, okay? Originally, people think about software IC, okay? And then you have hybrid language that's in between. That's the half imperative, half functional. That's actually F# or Scala language. Okay, Scala language is on top of the Java virtual machine. Okay, and then you have the functional programming language. That's Lisp language, ML language, Haskell language, Oracle. Okay, these are different languages. Okay, so functional programming is a functional paradigm in which we try to bind everything in pure mathematical function. So basically, pure mathematical function means you don't have loop. You don't have loop. So you have function F function called by G function. G function had 2 input with H function called by K function. So pure functional code. When you do programming, you don't have loop. You don't have loop. You don't have any while loop, for loop, anything. You purely just using call function, calling function for calling function. But can this work? Can this really work? Yes, it will work. It will work for any function that you originally written in the C language or C++ language. So basically, C language, we also call it iterative computing versus recursion. It was proven that anything that you done in iterative programming can be done in a recursive programming environment. Okay, so don't worry. Function calling function work. It just may not be as natural as the language that you know. So far, okay. So far, okay. So now that's actually we bind everything in pure mathematical function style. So you purely just function calling function. There is nothing else that you actually would do except the function calling function. It is a declarative type of programming style. It mainly focuses on what to solve in contrast to the imperative programming. Our main focus is how to solve. Okay, so how to solve, you use a lot of expression and statements and something. Then here we only purely using function call. Okay, and then but why should I use functional programming? Okay, number one, fewer bug. By functional calling function is fewer bug. Okay, and then code will be simpler. Okay, code will be simpler, and then easy to parallelize. Okay, and scale. So right now AI they want to do more functional programming and do more parallelization. Okay, my son was involved in the Berkeley's research project right now. Okay, what they do is let's see. Let's do is so, okay, with the professor is stoic car. Okay, and then they are doing parallel processing, cloud computing, parallel processing for AI. Okay, right now it's called AIPA. Okay, parallel distributed computing for AI at Berkeley. Okay, so I think that actually I'm okay. Yeah, it's actually called Rice Lab. Okay, and they are working on real-time intelligent computing. Okay, scalable and parallel processing. Okay, anyway, that's actually a side topic. So basically, taking advantage of functional programming is a parallelism. Okay, method of proven. Okay, well, okay, so actually that's what we want to see. That actually what functional programming bring to us. How can that help us in AI? Okay, so you need to know about functional programming's core concept, functional oriented, not object oriented. Okay, expression rather than statement, just a function call, function. Okay, algebraic topic, function calling function for domain model. Okay, pattern matching. You don't use loop, you use pattern matching to for the control flow. Okay, so these are the key concepts for functional programming. Okay, turn to know. You have so many turn to know in this chapter. Immutable data that cannot be changed. First class function that can be object, can be return value, can be parameter. We call it first class function. Recursion is function calling function. And then you can use it to replace any iterative computing. Okay, tail code optimization. Recursion is good, but actually the functional, when you do function code, you do have epilogue and the prologue. You need to have extra effort. So tail recursive function code will optimize the code. It actually good for the functional programming language compiler optimization. So we need that. And mapping, reducing, pipelining. These are the basic function application. Currying, you check up the higher order function and daily evaluation. So these are different terms that you need to learn in functional programming. Okay, don't get afraid. Okay, these are functional programming. We will go over it one by one. Okay, if possible. And then these are the features that we talk about so far. Okay. So now let's actually look at functional programming now. Okay, I'm not going to use these slides for now. Okay, these are too much. You probably still learning a lot of terms. So let's directly jump to recursion. Before we go for the functional programming, let's look at the recursion. First, recursion is sum. You want to calculate the sum from 1 to n. Okay, so that's given the n, right? And then we actually would like to sum from 1 to n. So basically, if actually n actually equal 0, okay, and then you return 0. Okay, the sum of n is 0. Okay, and then else you return. Okay, else you return n plus. Okay, sum of n minus 1. Okay, this is typically the way we write a recursive function, right? So let's print. Okay, sum of 10. Okay, so this one you should get 55. Wait, there is no answer. Let me see. Something wrong. Okay, something that's wrong one more time. Let me save. Okay, because I don't save, so probably that's the reason. So it's 55. Okay, so this basic recursive function, is that okay so far? Any question? Any question so far?
No.
So basically, you have the sum of 10 will call 10 plus sum of 9, right? And then sum of 9 will call 9 plus sum of 8, right? And you call 8 will call 8 by sum of 7. Keep going, keep going, keep going, keep going, until you do 1 plus sum of 0. Sum of 0, you got 0, and this one return 1, okay? And you go back to become 1 plus 2, become 1 plus 2 plus 3, something like that, okay? So this one is showing you the recursive, and we do not use any for loop, okay? And this one is a sum, okay? So next one, let's look at tail recursive version. So sum tail version. Okay, let me change the name for this sum. I forget to give it the W word. Okay, second one, we want to have a tail recursive function. So we do have a sum of actually n, okay, still n, but here we have an accumulator. Okay, accumulator. So if sum num equals 0, okay, we return the accumulator. We finish it. Okay, we finish. Okay, otherwise we return, okay, sum of n minus 1. Okay, accumulator will become n, okay, plus accumulator. Okay, this is the tail recursive version, and we define sum, okay, top. Let's call this one actually tail. Okay, let's call this one sum of n. Okay, you will call sum tail of 10 and 0, starting from here. Okay. We can call the first one as a helper function. And it's tail recursive. Okay. I'm sorry, this is n, starting from n, not from 10. Okay. And then we do print sum of 10%. Okay. Compared to sum, it's actually more line, but it has a tail recursive. Okay. Return some tail. Okay, 55. Okay. Any questions so far? What is the difference between this tail recursive version and non-tail recursive version? I made you. Are you okay?
Yeah, I'm good. I was gonna say that the same thing might be I don't know, just that wouldn't the sum tail one take longer than just the sum one?
No, it takes shorter. Compiler can optimize this.
Oh, okay.
But what's the main difference when we talk about tail recursive and non-tail recursive version? Okay, non-tail recursive version, after you call the recursive call, you still need to do arithmetic operation. So this one is not tail recursive. Okay. This one, you finish your calculation for recursive function call, your data directly return. So basically it's like your sum 7 call sum 6 call sum 5 call whatever, and it return. There's no extra n plus before it. No more operation. So compiler can directly scratch all the epilogue, directly go back to the top level. Is that okay? Then the performance can be as good as some sort of the iterative calculation. Instead of setting up function call and then return values assigned to some variable and plus n and then return to some other variable. So that epilogue would be much faster. Is that okay? That's the main purpose for the tail recursive. Any questions so far? I'm trying to give you the idea of where we start from recursive, okay? And then why we do this, why we want to have helper function, okay? And then you know that, okay, it's still functional programming. We still don't use any for loop, right? We still don't work on any for loop so far. No for loop, no while loop. If maybe, okay, if it's okay, if even in the declarative function, you do pattern matching. You match a certain function, so you decided that you go this way or that way. So pattern matching is actually okay. Pattern matching is okay. It's a part of functional programming. It's not like not okay. Pattern matching is okay. Okay. N equals 0 or n equals 5, that's okay. If the statement is okay. But loop we don't encourage. Okay. Now we have these two. Let's actually try another one. Okay. Now let's look at okay, we based on n, that's actually okay. Let's look at the array. Okay, let's assume that we do have an array. And then we want to traverse through this array. Okay, that's wrong. We want to traverse through this array, okay? Okay, let's change the name. Okay, this name is no good. Call it my array, okay? Okay, here I do have an array and I want to handle this array. Let's actually do traversal. Okay, I want to go through the array. Okay, so I got an array. Okay, and then I also got index. Okay, index. Let's call it I. Okay, index. Okay, I want to traverse through this array. Okay, one by one. Okay, so basically, if index equals okay, the length of AR, okay, and this one we will return do nothing. Okay, do nothing. Else, otherwise we will actually do what? We will do actually print. Okay, arrays index value. Okay, and then we actually will continue. Okay, we will call traverse or ARR. Okay, index +1. Okay, so here let's actually do one more thing. Okay, if actually index equals 0, we print okay. Let's see how this works. Okay, this one is traverse function. That actually call it traverse helper. Okay. Okay, so we just call this function traverse A. We will put the array into this function traverse A. Traverse A will call traverse function helper array 0. This means initially we look at the index 0 location, right? We call the traverse helper, and this is array. We started from there. So when it actually is equal 0, we print the left side brace and the data, and then 2, right? And then after that, we call traverse 1. We actually traverse helper 1. We go to the next data, and then we print comma data, and then we print comma data, and then we do comma data, and then we do gamma data. So, and then when we finish it, it get out of bound, we print the right side greater. So you will be printing out this format. Okay, so that's actually save this one, and that's wrong. This one, oh, okay. It doesn't allow this, but that's converted to string. Okay, not a problem. Not a problem. Okay, convert the integer to string. Okay, plus sign need to have a string. It doesn't take the integer. Okay, and then it actually is okay. Print it change line, but we don't want to change line, so that's actually put end equals empty string. Okay, so you won't change line. You won't change line with the end equals empty. Okay, let's try one more time. Okay. This one plus, okay, this one should be, let me see, index out of bound. Index out of bound. This one, we have this print, okay, I'm sorry. This one equals the length. We also need to do return. Okay. We need to terminate the function instead of continuing. Okay, this is correct. Okay, this is correct now. Okay. Any question so far? So basically, if we reach the end of the array, we print the right side angle bracket, also return. If you don't return, you will continue to calculate. That is wrong. Okay. So if the index equals 0, you print the left side they separate it and the first data, right? And otherwise you print comma 4, comma 6, comma 8. And once you reach the right side, you print your right side greater than, and then start the program, return. Okay? Is that okay so far? This is actually a traversal through the array. So traversal through array, you can print the every array data. You can set the data's value, right? You can set data's random value. So let's try another version. Okay, try another version. Let's actually try my array 2. Okay, so let me actually copy this one, paste. So this one, my array 2. Okay, so my array 2. Here, let me actually call it my helper 2. Okay, helper 2, helper 2. Okay, so we will do helper 2, but this one we don't print. Okay, this one we don't print. So this core, let's actually delete it. Okay, let's don't print. So this one, if it's equal array, we return, we do nothing. Okay, so basically this one we stop. Otherwise, we'll generate a random value for it. Okay, so let's do this. Okay, so let's do generate random value. So let's do A of the index will be equals to random int. Okay, so here I would like to import. Okay, random. So random that random int. Okay, and then 0 to 10. So this one we assign a new value to the array, each individual one by random value. Okay, so this one, let's call it traverse 2. Okay, and similar function we can use it to set every single element. Oh, I'm sorry, it's set, but I still need to print. Okay, so that's your at the end still print A. So it actually got a new value. Okay, got a new value on each individual elements. Any questions so far? So this is a traverse structure. You go through every index one by one, one by one, one by one. And we do not use, so this is used to replace the for loop. Without using for loop or while loop, we use a recursive function to do it. Okay. So now that's actually find maximum. Okay. Find maximum. Let's assume that we have a data. One, two, three, four, five, six, seven, eight, 9. Okay, let's assume that this is an array. We want to have the index of the maximum value. Okay, so this is linear search. So let's define a function called linear search. Okay, given an array AR. Okay, and then we do have a traverse index. Okay, that's actually I. Okay, we are going to go through this one, and this one is a helper function again. It's not original. Okay, now let's actually go through it. If actually we are going to have we need to keep track of the max and the maximum index. Okay, so here if actually index, okay, greater equal to the length of ARR, okay, we will return maximum index, the index that we want to have. That's the linear search result. Okay, otherwise we will return, okay, linear search helper. I'm sorry, here we need to do comparison. Okay. Okay, if actually ARR's index, okay, greater than the maximum, okay, the maximum should be equal to ARR's index. Maximum index should be equals to index. Okay. And then here we call ARR, okay, index plus 1. Max and max index. Okay. Okay, and then we define linear search ARR. Okay. And we call linear search ARR. Okay, 0. Okay, so print linear search. I'm sorry, this one should be returning -1 if you don't get it. Okay, I'm sorry. Let me see. This one is actually index. Okay. So this one should be started and maximum 0 and -1. Okay. Maximum. Okay, I'm sorry, it should be 0. When linear search of A, okay. Missing the okay, so you started with the maximum value of 0. If you include a negative, you can use a very small, actually a very small value, okay? And index you started from 0. That's actually your first possible linear value, okay? Okay, let's try this one. None. Okay, I'm sorry. Index greater equal this. Okay, let's see. How come it's none? Okay. This one, if actually array index greater than maximum got updated. Array index 0. Let me save. Okay, one more time. Sorry for that. Okay, it's still none. None means that you're not returning anything. So you have a linear search. Oh, okay. Here I should do return. I'm sorry, I'm missing. Forget to return something. It got a value, but it didn't return. Okay. 5. Okay. 5 means index 0, 1, 2, 3, 4, 5. Okay. 9 is at the index 5 location. Okay. This one tell us what? Tell us still you actually traverse through your array. Your index is running index, so check it one by one. Okay. If the value is bigger than the maximum, you replace it, right? Replace the maximum. If not, you keep running until you run out of array. You return the maximum index that you found. Okay. So this one actually, my array 2 and maximum, they are using the same structure over and over again to go through the array. Okay. What I want to say is that whatever you learn, the algorithm, linear search, binary search, okay, whatever search that you learn in the iterative world, when recursive, we can still get it. Okay, let's try another one. This one called binary search. Okay, let's look at binary search.py. Okay, recursive version. Okay.
Do you have this code uploaded at all? Or
Let me pass it. Okay, let me actually pass it one by one. Okay. Eventually, I'll actually send you, no problem. Okay, but let me put in the chat box. Okay, this one's the PUI. Okay, let me pass it one by one so you can take a look at it. Okay, sorry for that.
oh, there, cool.
Let me pass it one by one. Okay.
Yeah, thanks.
Thank you, Telephone. Let me let me know.
Yeah, I couldn't find them on the lecture.
I just make it today, so
Mhm.
I just make it today.
Yeah, if I can't type it in while you're typing it, I just get a screenshot and then go
Yeah,
back.
sorry. Okay, it's good. You let
Yeah,
me
no
know.
problem.
Okay? I give you one by one. Okay, this is the process you learn recursive function. Okay, I usually teach recursive function in this order.
Yeah, I'd like to really master recursive functions.
And you need that for this homework, okay? The homework we have. So now let's look at the binary search. So binary search, we know that the data is sorted. Okay, let's assume that we do have 2, 4, 8, 10, 12, 14, okay, and then 16, 18, 20. I use an even number on purposely, okay? So let's assume that we do have a binary search function. Okay, binary search function. And remember, we're still writing the helper function first. Okay, you do have an array. Okay, you do have the low and the high. Okay, 2 value. So let's assume that let's actually write a. I'm sorry. Let's actually write a linear version first. Okay, let's write regular binary search first. Okay, before we go into the so-called recursive function. Okay, so we do have array. And then we actually would like to see if the key is in there or not, right? So this one actually what happened is you have this data 2, 4, whatever, okay? Let's assume that we actually right now key is 7. So you start to look at the middle value. So 7 is smaller, you will check the right side, right? And you check the middle value 4. 7 is bigger, so you check the right, I'm sorry. You check the left side first, and then you check the right side. Right side, you check 8 is still small. You go this way, and then it's in here. Okay, it's in here. Okay. Anyway, that's actually binary search. So basically, you need to set up 2 numbers, low and high. So basically, okay, we look at the termination condition later. Okay, so low would be equal to 0. High would be equals ARR. The length of ARR. minus 1. Okay, this is low and high. And actually, so here you would have the low linear search. Okay, usually you do this. So here you do while, okay, low actually is that's then equal to high, no crossover. Okay. No crossover. If actually ARR's, okay, and here you say mean value equal to low plus high integer division by 2, okay, and your mean value equal to G, then you return mean value, okay, else if your ARR's mean value is greater than T, that means you are in the right side. In the right side, you do actually your data is in the right side. So your low would be equal to your mu plus 1. Okay. Okay, this is typical binary search. Okay. So let's put in binary search array A, okay, with 7. 7 would not found, okay. 7 would not found because we don't have 7 in the array. Okay, here that's actually 12. Okay, so 1 hit, 1 loss. One more time. So first one missing. Okay, 7 is missing, so you negative number. Okay. Second one, 12 is okay. Okay. Let's see. The missing number is wrong. Okay. The missing number actually is wrong. Let me check it. Okay. When mid value is greater than the key is on left side. So this one actually should be I equals min minus 1. Key is on the left side. Okay, this one is low equals min plus 1. Okay, let's actually check one more time. Okay, minus 3 is correct. Minus 3 actually is right here. Okay. Minus 1, minus 2, minus 3. It will show you where the 7 should be inserted. Okay. Minus 3 is correct. Okay, so this is binary search. Your normal binary search. Okay. So that what happened is like you do have 2, 4, 8, 7, 8, 10, 12, 14, 16, 18, 20. So we do binary search. We start with low over here, high over here. Okay, your low over here, high over here. Okay, so your first mean value you will check is 12. So 7, let's assume that we are searching for 7. 7 is smaller. We are only searching for the right side. So the right side, we move our high to here. So the second one high is moved to here. And then you check 4 is the next one you check. And 7 is bigger. 7 is bigger, we would only check the right side. So low will be set to here. And the mean value, next one you would check is 8. It's still smaller. Smaller, you move your high to here. So high and low now have a crossover. Your low is higher than low. Low is higher than high. So you know that the 7 is over here. Okay. So that's -3. We use a -1 -low to return the missing location. Okay. So this one is a binary search. You write it in while loop. Okay. And it's not recursive. It's not. Okay. So that's actually write another version as a recursive version. Okay.
Oh yeah, I was going to ask about that while loop, but I thought there weren't any loops in them, but now you're doing recursive.
Okay. When there is a crossover, okay, return -1 -low. Okay. That's the same as this one here. Okay. Otherwise, okay, this one is a recursive version, okay? And then we need, this one is a helper function. So we need to define, okay, fine. So this one is called it helper. Helper means that it has extra parameter, okay? Okay, so this one is a recursive version. So let me copy these two values. Copy these two functions. Okay. Same function, but here we change it to recursive. So this is the recursive version of the binary search. Okay. In the homework, we will use this. You need to write a binary recursive function using scheme language. Okay. One of the homework later you will need that. Okay. You need to do that. Okay. This one 7 we return nothing. Okay. 7 we return nothing. 7 we return nothing. Something wrong. Okay. This one should be -1. The last element. Okay. Try one more time. Let me save. Okay. Let's see. When high crossover, low greater than high is a crossover. We do that. Okay. Oh, here I'm missing return. Okay. Okay, correct now. Okay, let me copy this whole file for you. Okay. We will use, there's one homework you need to use a scheme language to do binary search. Okay, it will based on this Python version. Okay. So basically, you can compare the linear search version that I use a while loop to write it, and the version that I use no while loop using basic recursive function code. Okay, compare the difference. Any question? So any more complicated function or any more complicated program, I can still using the recursive to write it. Okay, no question. Okay, no problem. That's what I'm teaching today. Okay, but I think that we probably will end our recursive function discussion right here because we don't have that much time to go over the whole thing for recursive programming. Right? That's too much.
Can you put that code up there, that last code?
The last code I posted already.
Oh, did you?
Yeah.
Oh, cool. Thanks.
Yeah. I put on the chat box already. Okay.
Mm-hmm.
I will group them after class to send by email again. Okay. Don't worry.
Oh, okay. Thanks.
Don't worry. And here we need to end our discussion for recursive function. Okay. What I want to show today is that just like every code that you write in the iterative programming, you write C program, C++ program, whatever program you write, they always can be written by recursive function code. So let's go back to our fundamental idea of this chapter. Is functional programming. You need to use a function calling function. We are not allowed to use for loop in functional programming. Is that okay?
Mm-hmm.
That's a fundamental requirement because you are using functional programming to solve problem. You are not allowed to use for loop. No, you are not. You have to depend on the function calling function. So that's why we introduced this functional programming. Yes, question?
Actually, I have a quick question. When would you use functional programming over object-oriented? Because when object-oriented makes certain things just easier than functional.
Right.
There's a debate.
Okay.
There's a debate. So basically, people got used to object-oriented programming. They will say for it, right? And then people say functional programming is better. They will promote it. So basically, right now, AI prefer functional programming. That's why. If AI doesn't rise, I don't think that, okay. So this AI guy, they try to do functional programming, try to parallelize functional programming. So parallel functional programming by itself is a topic. Columbia has a whole class for it. Okay. It's a topic. Okay. It's a topic how to parallelize it. So you utilize your multi-core to get the parallel functional programming. Even Java, different course right now in the research community, they try to parallelize your functional programming code. So basically, what is the programming? Parallel processing. You can run this one and this one independently. Two different cases.
In two different threads.
Yeah, two different threads using the core to process it. Okay, that's the advantage of the functional programming. Okay, so that's actually goes to the slices. Okay, more. Okay, so basically, we can compare the iterative function call and the function, the regular code and the functional programming code. Okay, so right hand side you actually have a function, you have no side effect. Left hand side you do have the global variable, local variable side effects. Okay, and the right hand side is a function call. You apply lambda function to it. Maybe the lambda function, it will get a parameter x, and you will perform s squared. Okay, and this is functional programming. This is actually in Python. This one also in Python, but it's a regular for loop type to calculate the s squared for each element. Okay, so you apply this s squared value to every element of y, and when you print, this right hand side is the same as the left hand side.
Yeah, isn't lambda like replacing a for loop, or isn't that
lambda is a function?
Mm-hmm.
So this function will apply to y for every single element, and it's the mapping function's function. Is that okay? So you have a map function. This is a function call. You apply a function to the element here. Is that okay?
Mm-hmm.
So this is a higher order parameter. So you can, so what's the higher order function? You can pass the function as a parameter to the map function. So here, your map function is a function. Your map function is a function. And then you get the lambda expression. You get the lambda expression and your y, and your result would be the lambda function performed on the y. Is that okay?
Mm-hmm.
So your input is function data, output is data. Is that okay? Regular function call is that you do have a function, you get data 1 and data 2, you get data 3. So only data input, data output, right? If you run the Java functions like that. But Python function can take function as input. That's we call it higher order function. Is that okay? Both are Python. Left-hand side. That's why we use Python as a main language that we are using in this course. We do teach Java sometimes, we do teach Scheme sometimes, but primarily we are teaching Python because it provides both iterative programming and functional programming well. Okay. Next one, we do have mapping v times 5 function. Okay, and then there's a lambda function filtering. Filtering means that some x random number function and only modular 2, so only even number will be applied. So filter is another function that you only, filter is another function. I'm sorry, I lost it. So filter is another function. You use a filter function. So the data is a random 10 number, okay, but you only allow the even number. So only the x will only have 2, 4, 6, 8, those kind of numbers. Okay. R number will be filtered out. And then you apply v times 5 to it. So you will change to 10, 20, 30. Okay. Is that okay? So here you use a 10 random number, right? And then if it is an even number, you multiply by 5. If not, you keep the same value. This is what it is. Left-hand side, right-hand side the same. Right-hand side is functional programming, no loop. Left-hand side is Python, generic Python. Is it okay? Right-hand side and left-hand side get the same result, but right-hand side only functional code. This is functional programming. So higher order function, we have map, filter, and some other 3 functions. These are the fundamental function, map function, filter function, and there's one more reduce function. Okay, we'll talk about reduce later. But these 3 are the fundamental functional programming functions. So third one is reduce. Reduce is another one. So left-hand side is the getting a sum. Okay, and this reduce is actually you apply the sum to among them. Reduce is apply sum among the data. You have the x, so you apply sum among the data. That's called reduce. Is that okay? So right-hand side, left-hand side still getting the same result. Right-hand side, it actually is called functional programming. In the old day, they provide reduce as a standard function. It's actually Python 2.5. But now you put the reduce function into the functional tool, another module. Okay. But these 3 functions, map, filter, and the reduce are 3 fundamental functional programming functions. Okay. What does that mean? That means that these 3 functions, you do have map, you do have lambda function, and you do have data, and you provide lambda over every data, right? This is mapping every function to it. Second one, you do filter, right? You do have the function lambda and the function d. Okay. And then basically this one you also actually only actually the data will be filtered by the lambda. Okay. Only valid one will be applied.
So a lot of this can be applied to our term project.
Yeah. Yes. And you do have the reduce. Reduce actually is the lambda function. You have a d. So you apply the lambda function among the d together. Say your d may have a plus b plus c. As long as the function is plus, you sum them up, apply the function among them. Is that okay? These are 3 fundamental functional programming functions: map, filter, and reduce. And reduce right now move to the functional tool. So you need to actually import the functional tool. Otherwise, you won't get it. In the old Python 2.5, you get it directly. Okay. So partial function. So here we talk about a higher order function, map, filter, and reduce. Okay. And then we do talk about the tail recursive function before. Okay, this you know that. And then partial function, consider function ABC. You may use a function GBC, okay, and apply one. This we call it partial function code. So set some default value to some parameter, you get the partial function code, okay? Not a full function code. This is partial function. So these are the terminology. You need to remember what's higher, has no side effect, what's higher order function, what's tail recursion, what's actually partial function, okay? These are the topics that we say that we are going to cover here, okay? These are the topics we talk about that we would like to cover. Pure function side effect, okay? This different term. Okay, let's look at the next one. Tail recursion. Tail recursion is a function that you do not need to do mathematical operation after the function, okay? And then, okay, whatever. Pipeline, okay? Pipelining Python doesn't support it, okay? But some other functional programming do support it, okay? But anyway, pipelining is that you allow the function to be put into the pipeline and perform faster, okay? So here you see the functional programming, you do have many terminology you need to learn, okay? And then your function, this chart is like, in the old day, your function is only taking vector in, vector out. It's a regular function. Okay. Now you can take function in, vector in, function out. It's called function factory. Vector in, function out, and function in, vector out. That's called functional programming. So this one say map. Map is taking lambda function in, data out, right? Reduce is the same thing, okay? Function factory is you take the vector in, you actually generate a function out. Okay, let's look at this function factory. What is function factory? Okay, let's actually look at. There is a function called make adder, okay? So this is a function factory. Okay, this one is a function factory. So that's actually $11, okay? The result is 11. So let me explain it, okay? Let me explain it. So this make adder function is a function that would, this make adder function that will take a number n in here. This is data. You generate a function called G function. This G function will take in x and then return s plus n. Okay. So basically, make adder one take input of 1 over, create a function, this function called eta 1. You will return the value of x plus 1. So no matter what x generate, you will actually create x plus 1. So this one return a function. So eta 1 is a function. So you take input of the data, make eta take input of the data, but generate a function return. So eta 1 is a function. Eta 1 is a function, you will add whatever x you take, increase by 1. This is called function factory. Is that okay? And the function factory, there's a template. Template function is over here. So that's actually try different one. So let me actually create a new function called eta 10 and eta 4. You will make eta of 4. Okay, this one actually input 4, output eta function that increase by 4. Is okay? Input to the make eta is 4. Output is a function which will increase the data by 4. Okay, so that's a print. Okay, eta 4 of 6. Your input is 6 now, but your function is eta 4. You will increase by 4, so it's 10. This is called function factory. Make eta is a function that take in data but create function. Okay, so then another one is you can also take function in and generate function. So functional programming is not only taking data in, you can also take in function in, and also can generate vector or generate function by itself. It's a functional programming. Okay. Any question? You can return value, and the return value is a function. So it's so different from the OOP. Okay, you can comparison. And the key characteristic, you have map, filter, and reduce. Okay, we talked about it already. Okay, and that's functional programming. Okay, a pure function is a function whose output value follows solely from its input value. Okay, without any side effect. That's called pure function. Okay, pure function means you only depend on the input. There's no side effect. Okay, so you have the argument and return value as a function, but sometimes they are side effect. Side effect means that you store something, change some value or some extra efforts. Okay. Okay, and functional programming is higher level, is transparent and parallelizable. Okay. And different language will support it. So first-class citizen in Python, functions are first-class citizen. This means that function have a characteristic value, string or number is the same as that. Wherever you can return string, you can also return function. Okay, that's called first-class citizen. And they are second-class, third-class by different definition. So some other language function are not first-class citizen. You cannot return a function. Okay, for example, like Python. Java. Okay, Java you cannot return function as return value. Okay. Okay, these are okay. The first-class citizenship. What time we have? Okay, we are 11. Open function. And function chaining is you actually function calling functions for function chaining. Okay. This portion is Okay. Lambda expression is a function expression. Okay. You use it for shorthand purpose. Okay. And you can apply the function. So usually when we do functional programming, your lambda function can be used easier than you write a different function. Okay. That's a lambda function you can study. Okay. And then make function, we talked about it already. Filter function, we talked about it already. Reduce function, we talked about it already. Okay. Let me check what's still important in this chapter. Okay. Okay, we actually approaching the end. Okay. Any question today?
I have a question.
Yes.
I had always heard that recursion like really drops the big O notation.
Yes.
So do you want to use a lot of recursion or?
Yeah, in functional programming, we depending on recursive all the time.
So like what does your big O come out to be if you use a lot of recursion?
Depends. Depends.
I mean,
right?
like, aren't they using like a lot of data with functional programming?
Mm-hmm. It depends. It depends. I cannot tell you because it's actually case by case.
Oh, okay.
Here we can only tell you how recursive can be done nicely, right? As long as how much performance improvement, it had to be depending on the coding by itself, right?
Right.
We can predict that. So what I can only say is that you need to follow the good discipline for writing recursive function, then your parallelism would be high.
Yeah, because if you're using recursion with a great big list or a great big container,
if you don't follow, then you may not, right? If you don't follow the good recursive function principle, then you may not get good result. Okay.
yeah, I like how we're like cutting out the for loops and everything, and we're just doing it.
Yes, yes. And
with coding.
those different cases can be done by parallelism. Okay, you can apply to using multi-core to write the same function code. Okay, so next time we will still talk about recursive, and it will be recursive and tree. So this time we do not involve tree. Okay, so don't worry, we still have more functional programming coming up.
Good, it's interesting.
Okay, okay. Okay, so if no question today, we're up to here, okay? Thank you for coming over for this makeup session, and I feel happy for it. And then Monday, we go for another session, okay? We make up for one lost week. Thank you. Bye-bye now. Bye-bye.
Thank you. Bye.